Hello everyone, this is our presentation for the ANLP final project. The title of our project is GNNs for RAG chunking. I am Chinmay and my teammates are Ishan and Vishesh and we're CVITeam. So here's the agenda for the presentation. First I'll discuss the problem, then the current approaches, some motivation and intuition for our experimental hypothesis, then we give a brief overview of the pipeline. We discuss the evaluation metrics that we used and evaluated our project's performance on. Then we go to future directions and finally some of the challenges that we face during implementation. So the problem that we seek to address is to improve chunking in RAG or retrieval augmented generation systems. RAG has become the backbone of enterprise and academic LLM applications, from tax copilots to law applications and, of course, authenticity in academic contexts. Because of its widespread adoption, even incremental optimizations in the pipeline have a significant effect. And therefore, what we seek to optimize here is chunking, which is how a document is broken down and pre-processed before storing into the vector store for querying. This step is an important part, and improving it can lead to significant improvements in the whole RAG pipeline. So now we discuss some of the state-of-the-art approaches for this problem. The basic approach is fixed size sentence or character based chunking, where we just decide a specific predefined number of characters or sentences and we consider those directly as the chunks for the document. Then we had semantic and sequential chunking methods. Semantic chunking involves segmenting the document, and then we continuously do an agglomerative style of adding new sentences until the cosine similarity for the next addition drops drastically or the chunk size threshold is reached. We repeat this process until the whole graph is segmented. Sequential linear approaches consider the whole document graph, and they take a directed graph where each sentence sequentially flows into the next, and we again break it down wherever we have the predefined chunk size boundaries. However, the state of the art approach that performs the best is the recursive text splitting method. Here, we firstly segment the document graph based on paragraphs or thematic sections as discussed by the authors, and within each segment, if it is greater than a predefined chunk size limit, we recursively split it further. This can be defined by semantically relevant indicators such as punctuation marks or the ending of sentences, and this recursive splitting procedure is carried out until it is within the chunk size limit. So, the motivation for this project was the question, what even is a good chunk anyway? We realized that information is sometimes best structured in nonlinear ways, and human linear schemas, as given by the authors, are not necessarily the optimal ways of organizing the information within that document. As an example, consider this paper here where we have the abstract and the conclusion. There is a line in the abstract which is related to the conclusion. However, in a sequential linear schema, you would never see these being together. We wanted to build a non-linear document graph based approach that would allow us to have and account for such cases in our schema. And for this reason, we decided to take GNNs. So here is our pipeline. Firstly, we considered GNNs because simple linear combinations of a semantically based graph and a linearly sequential graph would not give us all the combinations necessary. This is because while they would average out in an affine way the global level properties, the local properties would not be averaged out, or we would not be able to create all possible combinations. GNNs allow us to consider multi-hop connections from k equal 1 to whatever, like the whole diameter of the graph, and by doing this they allow us to form non-linear combinations that involve information from both different graphs. So, as you can see the pipeline, we essentially used the semantic relations graph as the ground truth, and we used a graph sage architecture with a link prediction objective to bring the hierarchical linear graph as envisioned by the authors closer to the semantic graph. We use GraphSage because of its inductive learning capacity and the fact that a lot of these RAG systems are going to be used for industry applications where the document size is variable and changing. In such a context, inductive learning capacities where a neighborhood aggregation is considered instead of the whole graph end up being relevant. We also utilized link prediction with a binary cross entropy loss, and this essentially allowed us to predict the edges from the semantic relations onto the hierarchical linear structural graph. And by this gradual update process across different epochs, we end up with a non-linear combination of the structural and the semantic graph. Finally, this was clustered and stored, and we evaluated it on metrics for question answering and evaluation, which is the standard for RAG.
Creating graphs from documents, we used three different strategies. Semantic graphs were created by setting edge weights as the cosine similarity between sentence embeddings. Edges with weights lesser than a threshold were then removed. For structural graphs, we created edges between sentences that were adjacent to each other, in the same paragraph, or in the same section with varying weights. Hybrid graphs for baselines were created by taking a linear combination of the weights from the semantic and structural graphs. To create chunks from the graphs we had, we used agglomerative clustering. The RAG chunks were then taken to be these node clusters. For training, we used the ACL anthology corpus, consisting of over 70,000 papers from the field of NLP. For evaluation, we used the Casper dataset. It is a dataset used for question answering on research papers. We used a subset of the dataset for our evaluations, and in our pipeline, we create the vector database for one document at a time. Automated metrics from our evaluations are shown here. We can see the recursive text splitter being the best performing baseline. Hybrid graphs and our GNN pipeline output comparable results to existing character-based and sentence-based chunking methods. These are the results from running LLM as a judge for the evaluating on the answers. The LLM was provided the correct answer and the responses from using different RAG pipelines. The results from the evaluations are shown on the right. We can see that the GNN-based approach is comparable to the recursive text splitting and does better than than a simpler hybrid graphs we had.
Let's dive into the core findings of our research. First and foremost, we found that the recursive text splitter remains a state of the art strategy. Despite the complexity of our proposed models, the simple recursive approach is tough to beat. However, our GNN models successfully outperform the standard linear and sequential baselines, and we saw a consistent improvement in performance as we increased the amount of training data. One of the more surprising results was regarding hybrid methods. We found that combining structural and semantic weights actually led to worse performance than using either method purely on its own. These hybrid chunks often lack coherence. Additionally, we strongly suspect that the standard evaluation datasets exhibited a bias towards linear structures, favoring sentences that are physically close together, which naturally disadvantages non-linear non-sequential approaches like ours. Based on these findings, we have mapped out four key directions to take this research further. First and foremost, we need to conduct rigorous human evaluations. We suspect that automated metrics like Rouge and Blur are biased against our approach because they penalize non adjacent sentence retrieval. We need human reviewers to confirm if the GNN is actually finding topically relevant content or that the automated metrics are simply failing to recognize. Second, we plan to significantly upscale our model. In this experiment, we were limited by our compute to training on only a fraction of our available data. We want to run a larger GNN on the full dataset because our trend line suggests that with more training samples, the GNN's ability to capture semantic structures improves linearly. Third, we need to stress test the system with better data. We aim to work with evaluation datasets that feature longer documents and more complex multi-hop questions. This is where a graph-based approach would theoretically shine over linear chunking. Finally, we intend to move beyond our current architecture and perform ablations with graph attention networks, or GATs. Looking at the challenges we faced during our research, first was graph clustering. Initially, the clusters we generated from the graphs just grouped adjacent sentences together, effectively recreating the original paragraphs. We had to carefully tune the edge weights in the structural graph to mitigate this and force the model to find nonlinear connections. Second, we ran into major CUDA and memory issues. Our unoptimized training loop wasn't caching document graphs to the disk correctly, which led to frequent out of memory errors and limited the number of ablations we could run. Third, we struggled with the LLM generation itself. Early on, the model suffered from runaway generation and hallucinated outputs. We eventually stabilized this by enforcing a strict JSON output format. And finally, evaluation. Because standard-aware datasets are designed around linear chunking principles, applying them to a non-linear graph-based system made using standard retrieval metrics extremely difficult. So in conclusion, while recursive text splitting is still a very strong method for IAG pipelines, our work demonstrates that GNN-based chunking can beat traditional linear methods. More importantly, the trends show that with more compute and training data, the GNN approach improves significantly. We have made all our resources available for the community. You can find the code for reproducing our experiments on our GitHub, and our trained models are available via the Google Drive link. Thank you for listening.